So if we start on 1A, it says define the term oxidizing agents in terms of electrons. You know that an oxidizing agent gets reduced itself, and if you remember oil rig, you remember that reduction is gain of electrons. The fact that the oxidizing agent gets reduced itself means that this will gain electrons. And then question 2 a little bit more tricky. So it says identify the most powerful reducing agent in the table. Now, the most powerful reducing agent will get oxidized itself. And if it's being oxidized, it means it's losing electrons. So you've got to look up and down this table and look at which one is going to lose electrons the easiest. The one that's going to lose electrons the easiest is the one that has the lowest electrode potential, the most negative electrode potential, if you like. And one of the most negative electrode potential is this one, plus 0.77. You've also got to remember that all of these reactions are written for the reduction reaction. So actually, the most powerful reducing agent, or the one that's most likely to get oxidized, is this, because this equation has the lowest or the most negative electrode potential, but also you've got to switch it around because it's being oxidized rather than being reduced. So the most powerful reducing agent is Fe2+, and I apologise for the typo here, that should have been Fe2+, not F2+. Then it says identify the most powerful oxidizing agents. That is going to be the inverse argument. So the most powerful oxidizing agent is going to be the one that's most easily reduced. So that's going to be the one that gains electrons the easiest, and that's going to be the most positive one. So it's plus 2.15. Remember that all these equations are for reduction. So this time you don't have to reverse the equation, and so the most powerful oxidizing agent is F2O. Then it says identify all the species in the table which can be oxidized in acidic solution by BrO3-. So species just means substances or reagents or things basically. So it's just which ones of these can be oxidized. And if they're being oxidized, that means they're going to be losing electrons. They're going to have to be more positive than the BrO3- electrode. So here's the BrO3- electrode. That's got a electrode potential of plus 1.52. It's got to think of the two that are more positive than that, and that is if they're losing electrons, they're going to be more negative. I apologise. So identify all the species in the table which can be oxidized in acidic solution by BrO3-. That's going to be the ones that are more negative than the BrO3-, because if they're being oxidized, that means they're losing electrons. So BrO3- has an electrode potential of plus 1.52, and so the ones that can be oxidized are this electrode here, because that's more negative, and also this electrode here, because that's more negative as well. Now remember, if they're being oxidized, that means you've got to reverse these equations. So actually the ones that are most easily oxidized, or the ones that can be oxidized, are the ones on this side, Fe2+ and Cl-. So those are your answers there. So remember, the oxidation equation is the opposite of the equation that has been written up here. We move on. The cell represented below was set up, there we are. Deduce the EMF of this cell. So we've got two electrodes here, so we've got to first look up the two electrode potentials. So Fe2+ and Fe3+ is plus 0.77. And BrO3- and Br2 is here, plus 1.52. So we take one away from the other, and that gives us that equals minus 0.75. Remember, the polarity of this EMF, i.e. whether it's positive or negative, is based on of the right-hand electrode. So if we just look again at the table, the right-hand electrode is this BrO3- one. So if we look at the table, the BrO3- electrode here is more positive than the Fe3+ Fe2+ electrode. So actually, our EMF, if we're going to write it correctly, is going to be plus 0.75. Then it says write a half equation for the reaction occurring in the negative electrode. So the negative electrode is our Fe2 plus Fe3 plus electrode, and that, if we just look at the electrode potentials, we've got to work out whether it's being oxidized or reduced. So if we look at the two electrode potentials, this one is more negative than this one, so that means electrodes are going to be flowing from the Fe2 plus Fe3 plus electrode to the BrO3 minus electrode. So the Fe2 plus Fe3 plus electrode is losing electrons, therefore being oxidized. So we're going to reverse this one around, and so the equation is going to be Fe2 plus goes to make Fe3 plus an electron. And then, if we look at the next question, deduce what change in the concentration of Fe3 plus would cause an increase in the EMF of the cell. So we've got to think very carefully about this question. First thing we've got to think about is how can we increase the EMF of the cell by changing the electrode potential of this cell. Now the electrode potential of this cell is the more negative one, so if we can make this electrode potential more negative, then that will make this EMF bigger because the difference between these two numbers will be greater. To make the electrode potential more negative, we need more electrons on that electrode. And so we want to shift this, well this is an equilibrium, really. We want to shift this equilibrium to the right. And to shift the equilibrium to the right by changing the concentration Fe3+, we've got to decrease the amount of Fe3+. Because then the equilibrium will shift to increase the concentration again, and therefore also make more electrons, which will decrease the electrode potential and make it more negative. So the explanation here is the equilibrium will shift to the right, therefore making more electrons or releasing more electrons, which will decrease the electrode potential of the Fe2 plus Fe3 plus electrode. It's important you don't get the electrode potential and the EMF mixed up. The EMF is the difference between the two electrode potentials, but if you want to just talk about the charge, if you like, of one of the electrodes, then we call that the electrode potential. So next question. So this says, from the table above, select the species which is the most powerful reducing agent. So now we know the most powerful reducing agent is the one that's most likely to get oxidized. And if it's getting oxidized, that means it's losing electrons. So this is going to be, again, the most negative electrode. If we look down the table, the most negative electrode is the bottom one. But it's being oxidized, remember, because it's a reducing agent, so we've got to write the thing on the right-hand side of the equation, because if it's being oxidized, it's actually going the other direction. So again, this is Fe2+. Then it says, reduce the oxidation state of chromium. So oxidation states, hopefully remember from Chem 2. So the oxidation state here, first you've got to think about what the oxidation state of oxygen is, and each one of those 7 oxygens is -2. So all the oxidation states have to add up to -2, because that's the charge on the ion. If each oxygen is -2, then that equals -14. So for the charge to be -2, that means 2 chromiums must equal plus 12, and therefore 1 chromium will be +6 for its oxidation state. And then nitrogen in HNO2, then it's going to add up to 0 because there's no charge on this. Hydrogen is +1, oxygen is -2, and therefore nitrogen must also be +1 for it to add up to 0. Then it says calculate the EMF of the cell represented by that, so we've got to look at the two electrode potentials. So we've got Mn2 plus MnO4 minus, that one's this one here, so that's plus 1.51. And we've got to take the electrode potential of this one away, so S2O82 minus, that's the top one, which is plus 2.01. So that equals 0.5. That's the difference between them. We've just got to think about this positive or negative. Just got to think about the polarity of the right-hand electrode. The right-hand electrode is more positive than the left-hand electrode, and therefore this is a positive EMF. Then it says deduce an equation for the reaction which occurs when excess of S2O82 minus is added to an aqueous solution of Mn2 plus. So first we've got to think about which one is being oxidised and which one is being reduced. So we're again think about these top two equations, and the electrons are going to flow from the more negative one to the more positive one, so it's going to go that way. That means this bottom one is losing electrons, so that's being oxidised, and the top one is being reduced. So actually, this reaction is going in the opposite direction. And so then we can add these two things together, but only after making sure the electrons cancel each other out when we do. And to do that, we need to times the top one by 5, and we've got to times this bottom one by 2, so that both of them have 10 electrons in their formulae. And now when we add these two together, the electrons will cancel. So the equation is going to be, if we look at the top equation first, 5s2o82 minus plus, and then look at the bottom one now, it's going to be 2mn2 plus, because remember it's going in the opposite direction. Sorry, 2 plus. Make sure you, in an exam you scribble that out and start it again rather than doing what I've just done. Plus 8H2O, and that goes to make, if we now look at the other side, it's going to make 10SO4 2 minus plus 2MnO4 minus plus 16H plus 2MnO4 2 minus plus 16H plus. So there's your answer. Okay, next question. Use the standard electrode potential data given, so that's this stuff here, to answer the questions below. So calculate your method of this cell, so we've done that quite a few times now. So again, we look up these two electrodes. So this first one is H2SO3, so we're just going to find that one's here. So that's plus 0.17. Take away the other one, which is Fe3 plus. That's this one here. I assume Fe2 plus should be there as well. That's a bit of a typo. So that's plus 0.77. So it's 0.17 take away 0.77. So that equals 0.6. Is it positive or negative? We'll look at the two electrodes. The right-hand electrode is this one, and that is more positive than this one, so therefore again this is a positive EMF. Then right half equation of the oxidation process occurring at the negative electrode of the cell. So you've got to think about which one is the negative electrode. Again, look at them both. So that one is more negative than this one. So the oxidation process is going to be this, but in the opposite direction. Remember, the oxidation process is the other way round to the way it's written in the table. So it's going to be H2SO3 plus H2O goes to make SO4 2 minus plus 4H plus 2 electrons. Now you still need this table to answer the rest of these questions. So the cell represented below is under standard conditions. There we are. Write an equation for the spontaneous cell reaction. What that means is we've got to work out which one of these has been oxidised, which one's been reduced. So the H2O2 one is here in the middle, so that's plus 0.68, and then we look at the IO3 minus one, which is second from bottom, plus 1.19. So if we look at those two, electrons are going to flow from the more negative one to the more positive one. So this one's been oxidised, this one is being reduced. So the H2O2 electrode is going to be written in the opposite direction. But also it needs to be times by 5 because we've only got 2 electrons in this H2O2 formula, but 10 in the other one. And remember, they've got to cancel out, so we've got to times all those by 5 when we write it out. So we've got 5H2O2 plus the stuff on the left-hand side of the equation of the IO3 minus 1, so plus IO3 minus plus 12H plus goes to make, and the top one's been times by 5, so that's going to be 5O2 plus 10H plus I2 plus 6H2O. Now you can see we've got H plus on both sides, so we've just got to cancel those out, so we get rid of those 10, and this, instead of being 12H plus, is going to be 2H plus. says give one reason why the EMF of this cell changes when the electrodes are connected to current flows. That's because the concentration of the ions change, because when the current flows, they're basically being used up. And then state how, if at all, the EMF of this talent cell will change if the surface area of each electrode, pattern electrode, is doubled. That won't have any effect. If you change the surface area of the electrode, it has no effect, so no change. And then state how, if at all, the EMF of this cell will change if the concentration of IO3- ions is increased. Explain your answer. So again, we've got to think about how this will affect the number of electrons on this electrode. So it says the concentration of IO3- ions is increased. We're going to look at this electrode here. If we increase the number of electrons, increase the concentration of IO3-, that will shift this equilibrium to the right, which will decrease the number of electrons on this electrode, and therefore this electrode potential will increase because it will become more positive as the electrons are reduced. So if this is becoming more positive, that means the difference between these two things will increase, and so the EMF of the cell will increase. And again, you explain it through like Le Chatelier's principle. So equilibrium shifts to the right, more electrons used up, so electrode potential of IO3- electrode increases or becomes more positive. And then an excess of acidified potassium manganate was added to a solution containing V2+ ions, and you've got to use this data to work out what the vanadium species is present at the end. And all you've really got to work out there is whether this V2+ will be oxidized or reduced by acidified potassium manganate. First, you've got to look at those two reactions. So there's V2+, and manganate is down here. So manganate is plus 1.52, and V2+ is minus 0.26, sorry. So electrons will flow from V2+ to the MnO4-. So that's going to get oxidized to V3+. Now you've got to look then whether that will get oxidized further. So you can see V3+ is also here in the table. That's plus 0.34. Again, that is more negative than 1.52, so that will get oxidized to VO2+. Then look at VO2+, which is here. That's plus 1, and manganate again is more positive, so that's going to get oxidized again to VO2+. So that is your final species there. So final species is VO2+. The oxidation state, well, both oxygens are -2. It's got to add up to +1 because of this charge on the ion, so that's going to be +5. And the half equation is V2+ going to, that's what you started with, V2+, that's in the question, going to VO2+. So you've got to balance this like you would from Chem 2. So first balance the V's, they're already balanced. Balance the oxygens by adding water. It's going to add 2 waters onto this side because each water has only 1 oxygen. Then balance the hydrogens by adding H+, and then balance the charges by using electrons. You can see the charge, overall charge on this side is 2+, based on this vanadium has 2+, and the water is neutral. Overall charge on this side is 5+ from the 4H+ and the 1 VO2+. And then therefore you will need 3 electrons on this side to balance the charge. Finally, question 5 says, name the standard reference electrode. So that's the hydrogen electrode. And you've got to think about what conditions the hydrogen electrode is under. Now, platinum electrodes aren't conditions. That's just what is used for the electrode. But it might ask you that in an exam, but you've just got to be aware that isn't a condition. So the conditions are temperature, which is 298 Kelvin, pressure, which is 100 kilopascals, and then concentration of acid. So the concentration of acid, or concentration of H+ ions, has to be 1 mole per dm cubed. So you could say using 1 mole per dm cubed of HCl, or you could say half a mole of dm cubed of H2SO4. The next question, a cell is reduced when these two half cells are connected. Deduce the cell potential E, don't really know what to call that sign, for this cell, and write an equation for the spontaneous reaction. So this is essentially the EMF value. So you've got to look at the difference between those two things. Actually, no, sorry. Sorry, yeah, it is asking for the EMF value. So you've got 2.01 minus 0.8, which equals 0.21 volts. And then the equation, you've got to think about which one's being reduced, which one's being oxidised. The electrons are going to flow from the more negative one, which is the bottom one, to the more positive one. So the more negative one is being oxidised because it's losing electrons, top one's being reduced. So this one, bottom one, is going to go in the other direction. You've also got to multiply it by 2 because this one, bottom one, has 1 electron, but the top one has 2 electrons, and those have got to cancel. So you're going to have 2Ag plus S2O82 minus goes to make 2SO42 minus plus 2Ag. So it's just 1 plus, isn't it, if you look at the equation. And then finally, we've got another one of these equilibrium questions. So it says, state how if it's all the electrical potential of S2O82 minus and SO42 minus equilibrium would change if the concentration of SO42 minus was increased. Explain your answer. So if SO42 minus was increased, that would shift the equilibrium to the left-hand side to reduce that increase in concentration, and therefore more electrons would be produced, and therefore the electropotential would decrease because it would become more negative as more electrons are produced. And the explanation is equilibrium shifts to the left, and therefore more electrons released. Now notice this question is just asking about the electropotential of one of the electrodes, and so we can just leave it there as being more electrons released. But before it was talking about how it affects the EMF, and so there you've got to talk about how it affects the electropotential as well, because then it will also affect the EMF. I hope all that helps with your homework. Please let me know if there are any of those questions which still don't make any sense.